Hello, our project is using differentiable weighted finite state transducers in automatic speech recognition tasks. Our team name is Local Minimum, and I'm Shivan. I worked with Jani, Aditya, and Daniel on this project. So, weighted finite state transducers are a commonly used tool to encode probabilistic models. Previously, WFSTs are often trained using rules such as weight determinization, weight minimization, and weight pushing algorithms, which don't really employ any learning algorithms. So differentiable WFSTs are a recent development. There really hasn't been any extensive investigation into possible applications for various ASR tasks. So this process for differentiable WFSTs has been implemented in a framework called GTN. Much like how PyTorch has AutoGrad, GTN has its own version of AutoGrad that works with these WFSTs. So, implementing CTC loss using differentiable WFSTs is a good first step, attempting to improve upon the current methods available. This is significant because of the cutting-edge nature of these differentiable WFSTs, as well as novel because this project aims to make types of CTC losses proposed in the paper for GTN. The task for this project is to implement the CTC losses using GTN that were proposed in the paper. The dataset that we chose to test our models upon was the CMU's AN4 dataset. AN4 is much smaller than the LibreSpeech corpus, which is used in the GTN paper. This would mean much faster training and testing time, which would be useful because we were going to be using our local machines and AWS instances. It only contains 948 training instances and 130 test instances, and most of these samples are only a couple seconds long at most. All of the samples contain small readings that are not really complete sentences. It's mostly spelling words or saying numbers, and LibreSpeech is a little bit different since it contains full sentences from audiobook readings. This was done primarily to put more grammatical constraints on the WFSTs since the dataset is specific enough that specific grammars can be encoded into the transducers. So here are some of the different types of CTC losses that were described in the paper. These are all sample graphs for the word A. As you'll notice, there's two graphs for each CTC loss because of the two different pronunciations. So it could be said as A and A. So those two different pronunciations, that's why there's the two different graphs. Normal CTC loss, as you can see, does not constrain the repeated phenomes at all. You can see that repeated transition of A to itself on 4 and A to itself on 1 for that leftmost graph. For duration limited CTC, it limits the repetitions to just a set number. So in the case of the graph shown, it's only 2. You see that graph does not have that self-transitioning state. And then thirdly, there is the spike CTC, which does not allow any repetition at all. So as you can see, it's just the normal CTC loss without the transition to itself. So the approach is fairly straightforward. So GTN is made so it can interface with other machine learning frameworks like PyTorch. So using that knowledge, standard PyTorch model can be used, and at training time, the outputs can be fed into the GTN CTC function, like a normal loss function would be used. So a word graph from the previous slides, so any one of those CTC loss graphs can be composed with the emission graph that's shown here as the topmost graph. And that emission graph is used to constrain the weights to be like kind of standardize them. And composing those two makes a new composed graph. From this new graph, the loss can be found, and that can be used to update weights during the GTN backward. So our evaluation metrics include character error rate, computational time, and number of parameters. Unfortunately, we currently do not have any results at this time, but we expect to compare these models in the final report. And thanks for watching.